Okay guys, this is the next chapter of my videos about the spanning tree protocol. Today we will cover rapid spanning tree protocol. Disclaimer: all image that I use in this video is from How to Master CCNP Switch book by Rene Molenaar and some Huawei documentation. This video is part of my training to attend an interview test. Before we discussing about the RSTP, let's assume and make sure you know about the disadvantage of the STP. The first is the first disadvantage of the STP is the port states are not sharply distinguished. Which is not conducive to the learning and deployment for beginners. A network protocol that sharply defines and distinguishes different situations is likely to outperform the others. For example, listening, learning, and blocking. These three states do not forward user traffic and are not even slightly different to users. So 3 of these states are not forwarding user traffic. The differences between port in essence never lie in the port states but the port roles from the perspective of use and configuration. It is possible that the root port and the signature port are both in the listening state or the forwarding state. Okay, next, the STP algorithm determines the topology change after the time set by the timer expired. What it means? If the STP algorithm determines topo change after the time set by the timer timer expires, it will slow down network convergence. Okay, and the next, the STP algorithm requires a stable network topology. What this means? The STP algorithm requires stable network topology. After a root bridge sends configuration bpdU, the root bridge send config bpdU. Other devices process the configuration bpdU so that the configuration bpdUs are advertised to the entire network. This is also slow down the topology convergence. So the point 2 and the point 3, both of them slow down the topology change. That's why we are not recommended to use the STP anymore. Next, the advantage RSTP over the STP. Okay, the first advantage of RSTP over STP the RSTP deletes 3 port states and adds 2 port roles. You can see here in the classic spanning tree there are 4 states. They are blocking, listening, learning, and then forwarding. But in the rapid spanning tree, blocking and listening, both of them grouping into discarding, and then learning, after that forwarding. In my humble opinion, before blocking there are disable. So disable blocking and listening, both of them in the rapid spanning tree are discarding. After that, learning and forwarding. And for the STP, the port roles, there are root port, then and there are designated port, also the blocking. But in the RSTP there are adds two port rows, uh, alternate and backup, alternate port and backup port. Alright, that's for the point 1. And the second point, RSTP enhance the features and the protection. The protection that we will cover in this discussion is root guard, bpdU guard, loop guard, and TCP attack guard. Okay, this is the sample of the RSTP topology that we were all discussing about. So the first, we will know that switch A as the root bridge because they have the lower MAC address, and all the switch in the network topology have the same priority. So we will discuss about port rows in this diagram. So in the RSTP, same with the STP, in the root bridge, all the ports in the root bridge becoming designated port. Okay, and in the non-root bridge, in the non-root bridge switch, the port that directly connected to the root bridge will becoming the root port. Okay, and then if we are fetching the two switch, for example the switch B and the switch C, we will decide whether both of the switch will become the blocking port. Okay, we will cover root port, designated port, and we will discussing about the next port in the RSTP, alternate port and backup port. Okay, this is the blocking port in the RSTP. We call it the alternate port. Why the alternate port is state in the interface FA0/16 on the switch C, because the switch C has the higher MAC address than the switch B, and both of them have the same priority. Okay, the alternate port is done, and then the next we'll discussing about the backup port in the RSTP. What is the backup port? So the backup port is to back up the designated port. If we have two ports like this, for example FA 0/16 and /17 in the switch B, and connected to the switch C that have a MAC address that higher than switch B, so automatically all port in the switch C that connected or facing to the switch B becoming the alternate or blocking, and one of the switch B port, that is FA0/17, become the backup port, because designated ports already state in the interface FA0/16. So when this port is down, the backup port automatically convert to designated port, fell over. That's it. The backup port in the RSTP is to backup the designated port. Okay, in this slide we will cover about the RSTP bpdU. The bpdU is different from rapid spanning tree. In the classic spanning tree, the flag fields only had 2 bits in use, topology change and topology change acknowledgement. If in the STP, topology change and topology change acknowledgement, all bits of the flag field are now used. The role of the port that originates the bpdU will be added by using the port role field. It has the following options: unknown, alternate, or backup port, root port, and designated port. This new bpdU is called a version 2 bpdU. Switches running the old version of spanning tree will drop this new bpdU version. In case you are wondering, rapid spanning tree and the old spanning are compatible. Rapid spanning tree has a way of dealing with switches running the older spanning tree version. Let's walk through the other stuff that has been changed. Okay, we're going to the next slide. bpdU in the RSTP send every hello time. Wow, this is quite surprise for me, because in the previous STP or classic spanning tree, those were relied by the non or root switches, because only the root bridge generated bpdU. In the non-root switches, if they receive it on their root port, but different with rapid spanning tree, all switches generate bpdU. So if in the STP only RB that generate bpdU, but in the RSTP all switches generated bpdU every 2 seconds or every hello time. That's the first point. That's very interesting to discuss today. And then bpdU used as keep alive mechanism in the RSTP. The classic spanning tree use a max edge timer, which is 20 seconds for bpdU before they are discarded. So when in the STP they are using max edge timer, which is 20 seconds before they are discarded. In the rapid spanning tree or STP is very different. bpdU are used now as keep alive mechanism, similar to routing protocols like OSPF and IRGP maybe. If a switch misses 3 bpdU from a neighbor switch, it will assume connectivity to the switch has been lost and it will remove all MAC address immediately. So in the RSTP, okay, if a switch misses 3 bpdU packet from the neighbor, it will be assumed that the connectivity has been lost. Okay, it's very interesting that bpdU in the RSTP acting like keep alive mechanism in the routing protocol like OSPF, EGRP. And then the next interesting point in the RSTP is the RSTP will accept inferior bpdU. This is very opposite when we're talking about the STP, because the STP will be ignore the inferior bpdU. The transition speed or convergence speed is the most important features of rapid spanning tree. The classic spanning tree had to walk through the listening and learning state before it would move an interface to the forwarding state. This took 30 seconds with the default timers. The classic spanning tree was based on timer, while the RSTP doesn't use timer anymore. They are using the negotiation mechanism that will be discussion further in the proposal and agreement mechanism in the next slide. Okay. Okay, this is the RSTP config bpdU. It's quite interesting and quite very awesome. The value of the type field is no longer set to 0 but 2. RSTP capable device always discard the config bpdU sent by an STP capable device. Okay, this is the TCA bit 7 and bit 0 is the topology change flag. This is a proposal, port role, learning, forwarding agreement. So why we will talk in the next slide. We will talking about the proposal and the agreement. The 6 bits in the middle of the original flash field are reserved. Next, the protection function. What is the bpdU guard, root guard, loop guard, and TC bpdU guard? Okay, the first one we will discussing about the loop guard. Okay. Okay, the loop guard. What is loop guard? Okay, based on our picture, our topology, imagine the links between the switches are fiber links. Okay, this is fiber, this is fiber, this is fiber. In reality, there is a different connector for transmit and receive. Switch C here is receiving video from switch B. Okay, as a result, the interface has become alternate port and is blocking mode. Here, talking about the RSTP. After comparing all the priority and MAC address, switch B and switch C, this port, for example, FA0/16 will become alternate and blocking mode. With one requirement, this port must receive the bpdU from the switch B. Okay, this the very must requirement. If not, this port will become forwarding. Okay, we will discussing further. Next, this image. Now something goes wrong. The transmit connector on the switch B towards switch C maybe was eaten by mice. Failed to unknown reasons. As a result, switch C is not receiving any bpdU from switch B. Okay, switch C here doesn't receive bpdU anymore from switch B, but it's very odd because switch C still can send the bpdU to switch B. So this port will become forwarding and the unidirectional looping is happen in this network topology. That's crazy because switch C is not receiving any more bpdU on its alternate port. It will go into forwarding mode in this topology that's become designated port. We now have a one-way loop as indicated by the green arrow. Okay, here green arrow, here is the one-way loop, always doing the same on one-way loop. One of the methods that we can use to solve our unidirectional link failure is to configure loop guard. Okay, this is our solution to fix this issue because the one-way loop. When a switch is sending but not receiving bpdU on the interface, loop guard will place the interface in the loop inconsistent state and block the all traffic. So the port D, they not receiving bpdU anymore but still can send the bpdU. But if we configure loop guard on this interface or the globally configuration in this switch C, this port will block all traffic. As a result, the one-way loopback will fix it. Okay, that's why we need the loop guard in this scenario. Okay, the next we will discussing about the bpdU guard here. Sorry, yeah, this is the bpdU guard. Previous loop guard is done, and the next we will cover the bpdU guard. In this topology, by default spanning tree will send and receive bpdU on all interfaces, right? We have a computer on the FA0/2 interface on the switch B. Yeah, this computer. Someone with curious hostile intentions could start a tool that generates bpdU with a super bridge ID or the lower priority, because the switch A root have a priority 32, 76 and 8. So if this PC bpdU is coming to the root bridge, for this example the switch A, the root bridge is moving to this PC. This is very dangerous. So what will happen is that our switches will believe that root bridge can now be reached through switch B, and we will have spanning tree recalculation. Doesn't sound like a good idea, right? Very dangerous. So here, the hacker PC or the PC of the previous topology will become the root. Wow, that's very crazy. And the switch A becoming non-root, switch B becoming non-root. You could even do a man in the middle attack without anyone knowing. Imagine I connect my computer to the switches. If I become in the root bridge, all traffic from switch A or switch C towards switch B will flow through the PC hacker, where we run, we'll shock, and wait till the magic happen. We get all this traffic and the data from the wire shock. So what you can do, we must implement the bpdU guard in the interface. Sorry. So to prevent this attack from this hacker PC, we must configure the bpdU guard in the interface of switch B that facing through the hacker PC. Previously, maybe we configure this port as the edge port. Once they receive the bpdU packet, they will be from edge port become the non-edge port. As a result, the switch will be doing the recalculate STP, so the root bridge will move to the hacker PC. So back to the topic, this port we configure the bpdU guard. So after we configure this bpdU guard, this port will not accept bpdU anymore. That's our solution for this case. Okay, the next case is maybe a little different, but still the same with the bpdU guard. Is the root guard. What is the root guard? This case happen when we have an STP network, for example here. All the priority is the same, 32, 76 and 8, with the lowest MAC address in switch A. This switch becoming root bridge, but there is a switch D that have a lower priority than the three switch network. They have priority 40 and 96. So to prevent this switch D becoming the root bridge, we must configure the 0/16 on the switch key to root guard. We must enable this in that interface, because if we not configure that root guard on that interface, the switch key will become root bridge. Okay, the last but not least, the TC bpdU attack guard. So what is TC bpdU attack guard? So make sure you understand about the TC bpdU. So what is TC bpdU? So after receiving the TC bpdU, after the switch receive the TC bpdU, a switching device will delete its MAC entries, and ARP entries. Okay, this is the concept number one before we jump into the TC bpdU attack guard. So if the switches receive the TC bpdU, it will delete its MAC entries and ARP entries. But in the event of a malicious attack by sending bogus TC bpdU, a switching device receives a large number of TC bpdU. What happens when a switch, maybe for example they receive a large amount of TC bpdU? What will happen? The switch will be basis itself deleting its MAC entries and ARP entries. As a result, the switching device is heavily burdened, rendering the network rather unstable. So this is very dangerous if there are TC bpdU attack coming into our switch. So we must configure the TC bpdU attack defense or TC bpdU attack guard configure. Make sure you configure that TC bpdU attack guard or defense. Okay, the next topic is the proposal and agreement mechanism in the RSTP. So the key topic of this proposal agreement mechanism is to help a designated port to enter the forwarding state as soon as possible. Theoretically, STP can quickly select a designated port. To prevent loops, STP has to wait for a period of long time enough to determine the status of all ports on the network. All ports can enter the forwarding state at least one forward delay later. But RSTP is developed to eliminate this bottleneck by blocking non-root ports. To prevent loops, by using the PA mechanism, the upstream port can rapidly enter the forwarding state. Okay, as you can see here, the PA mechanism is worked by blocking non-root ports. This is blocking. Leave the port status unchanged. Leave the port alternate port. So the goal is to help designated port. This is the designated port to enter the forwarding state as soon as possible. So for this image, which you can see here, the P0 and P1 become designated port and send RSTP bpdU. After receiving an RSTP bpdU with higher priority, P1 determines that it will become a root port but not a designated port. P1 then stops sending RSTP bpdU. This is the root port. After receiving an RSTP bpdU with proposal field being 1, S2 set the sync variable to 1 for all its ports. S2 set sync variable to 1. For all its ports. As P2 has been blocked, its status keep unchanged. P4, this is an edge port. and doesn't participate in calculation, therefore only the non-edge designated port P3 needs to be blocked. This is needs to be blocked. After P2, P3 and P4 enter the discarding state, their sync variable are set to 1. The synced variable of the root port P1 is then set to 1. Okay, and P1 sends the RSTP bpdU with agreement field being 1 to S1, except for the agreement field which is set to 1, and the proposal field which is set to 0. The RSTP bpdU is the same as that was the 7. After receiving this RSTP bpdU, S1 identified it as a reply to proposal that I just sent, and P0 immediately enter the forwarding state. This proposal agreement negotiation process finishes, and switch 2 continues to perform the proposal agreement negotiation with each downstream device. Okay, I think that's all the short explanation about the proposal agreement mechanism in the RSTP. Okay, the last discussion in the RSTP is the RSTP topology change. What is RSTP topology change? If a non-output changes the forwarding state, the topology change. That's the key of this topic. After the switching device static, the topology change, it performs the following procedures. The first is start a TC while timer for every non-edge port. Starts TC. The TC while timer value doubles the hello timer value. Double the hello timer. All MAC address learned by the port whose status change are cleared before the timer expires. The port send RSTP bpdUs with the TC field being 1. Once TC while timer expires, they stop sending RSTP bpdU. Port send RSTP bpdU with the TC field being 1. Okay, once TC timer expires, they stop sending RSTP bpdU. Stop sending. Okay, that's for the point 1 and point 2. After another switching device receives the RSTP bpdU, it clears the MAC addresses learned by the all ports, including the one that receives the RSTP bpdU. The device then starts a TC while timer for all non-edge port and the root port, the same as the preceding process. In this manner, RSTP bpdU flood the network. Okay, that is for RSTP topology change. Okay, the end of this topic, interrupt RSTP and STP. When RSTP switches to STP, RSTP loses its advantage such as fast convergence. On a network where both STP capable and RSTP capable devices are deployed, STP capable device ignore STP video. So you must know that STP capable devices ignore RSTP bpdU. If a port on RSTP capable device receives a configuration bpdU from a STP capable device, the port switches to the STP mode after 2 hello intervals and starts to send configuration bpdU. In this manner, RSTP and STP are interoperable. If port, okay, I reply again. If a port on an RSTP capable device receive a configuration bpdU, okay, they receive config bpdU from an, so this is the RSTP capable device. They receive config bpdU from an STP capable device. This port, okay, switches to the STP mode. From the RSTP will become to STP mode after 2 hello intervals, and start to send the configuration bpdU. After this, send the config bpdU. In this manner, RSTP and STP can interoperable. This is interoperable. After STP capable device is removed, Huawei or another switches such as Cisco RSTP capable devices can switch back to RSTP mode. Okay, I think that's all our discussion about RSTP today. Thank you for watching, and I will upload another discussion about MSTP, IGP, SPF, SIS, and BGP, and also the MPLS. Thank you.